Hi again. We are going to be taking a step back a little bit. I know that you recently learned about how to create a confidence interval for mu and for p, but what's going to happen in practice in reality before even doing that, when you are starting a study, you're going to be asking yourself, or your boss might ask you, how much data, how many subjects do you need? And so I'm going to introduce you to one way of figuring out what the sample size should be for whatever it is you want to make an inference about. And so the way that you get or figure that out is the same reasoning, whether you are making an inference about mean or about proportion. And so over here, I am going to talk you through the derivation. I'm not going to quiz you on it, but it may be helpful to figure it out, because this way, if you can't find it on the formula sheet, if you understand where it comes from, it's pretty easy to recreate. So if you are making an inference about a mean, about mu, what you want to do is set the margin of error to a desired amount. And I'm going to call that epsilon, or this little e symbol right here. And then solve for n. That's really that all goes into it. So in step one, I set e equals z star sigma over root n equals epsilon. So I set it equal to epsilon. That's step one. In step two, I start solving for n. So the first thing that I did is I multiplied both sides by root n. That's going to get rid of the root n underneath the sigma, but it's going to multiply epsilon by root n. And so that is step two over here. Then I divide by epsilon. So that gives me root n alone. But then to get rid of the square root, I want to square both sides, and that gets me to the final formula. And if you happen to memorize this, that's fine. But if you're uncertain if it's right, again, that is the quick derivation for it. What about if we want to make an inference about p? The reasoning is the same. Set the margin of error equal to some desired amount, which I'm calling epsilon for general. Then divide by z star first. That's what I'd recommend. And then I would say square both sides to get rid of the square root. Finally, you could take the, what did I do? Multiply both sides by n. And so when you do that, you got n times epsilon over z star squared equals p hat q hat. And finally, divide by epsilon over z star squared, which is the same thing as multiplying by the reciprocal z star over epsilon. So that's flipped in the final answer over here. Now, if you happen to read the book or you look at the formula sheet, you're not going to see hat over the p and q. You're going to see it like the box in blue. So it's a small change, but here is what you would do. If you happen to know p, then use its value. And on practice, you wouldn't know it, because if you knew it, why would you want to try to estimate it? And so if you don't know it, but you happen to have an estimate for it, whether it was in a pilot study or some past research that's relevant, then use that estimate for P, plug it in. But in the worst case scenario where you don't know anything about it, then let P hat, or let P be 0.5. So that's the thought process. If you have P, use it. If you don't, but you have an estimate for it, then use that. And if you don't even have that, then just let it be 0.5. And remember, if P is 0.5, then Q is also 0.5 because it's 1 minus P. So those are the formulas that we're going to need. Now, for demonstration, I am going to go back to the confidence interval handout. And so let's go back there. And I'm going to fictionally change some of these problems. We're going to take a look at problem 3 here. And I am going to say, well, maybe the error wasn't quite what I am willing to accept for problem 3. Whatever 2.861 times 5 over the square root of 20 is, that might have been too much or too little. And so what I really want is I want that error to be 1.5. Now, this is something that either you would think about and assess as being good for you, or your boss might tell you it's not something that was calculated. It's essentially something that was given or reasoned through. And so if the error should be no more than 1.5, then I'm going to go through the whole process over again. So I am going to use the mean version, which we had calculated before. But remember, for problem 3, we didn't have sigma, we had S. And so I'm going to use S as an estimate for sigma here. And so we have 2.575 for Z star, S is 5, epsilon is 1.5. That's the desired amount of error, no more than that. You plug in, you square, and finally you round up. You always round sample size up, even if this was 73.01, and that's closer to 73, you round up to 74. So check the calculation, make sure you're able to do this in your calculator, but that's where the 74 came from. And before we go into another example, some of you may be wondering, well, if I'm using S, why am I not using T star? And if you think about it, you'll realize, well, if I was using T star and I need to find it, that table requires degrees of freedom, and degrees of freedom is n minus 1. But the whole point of what we're doing here is we don't know n. And so you can't find a value for a concept that's dependent on that value. So that's why even if you don't have sigma, you're going to estimate using Z star. Right? So if you weren't sure why I didn't make that switch here in the formula, that's the reasoning. Let's look at another one. So I'm looking at problem 2 here. And maybe in this case, we would accept an error of 1. Now this is another one that's making an inference for mean. And the error was too big here. And so maybe I want it to be 1. And let me think. Yep. So I want it to be 1. And using the version of the formula, we've got Z star is 2.575. So I kept 99% confidence. The standard deviation was given in this one to be 1.5, and epsilon is 1. So I plug that in, don't forget to square, and round up. So I got 14.9. You round that up to 15, and that's the final sample size. Right? So the original sample size was 50. And so if we are willing to have more error, then we could have less data. And that should make sense, because the more data you have, the more accurate you should be. And so the original error of 2.575 times 1.5 over the square root of 50 was likely very small. And maybe I thought, okay, well, that's too precise. I don't need it that good. And now I only need 15 subjects. What about for problem 1? All right, so for problem 1, over here, in this case, maybe I desire the error to be 2. And so what I'm going to do is the same process that we've been going through, Z star times sigma over epsilon, square all that, and find out what that is. And so Z star is 1.96. The standard deviation was 13.89. 2 is our desired error. Multiply, divide, and square that, and we've got 185.3, which means my final answer is 186. And remember, you always round up. 186. And so in order to have less error, which is what's going to happen in this case, we want more data. And so that should make sense. What about if we were doing this for proportion? And so let's take a look at number 4. If you're doing this for proportion, and maybe our epsilon or desired error is 0.2 in this case, and let's also change our confidence level. So now we're willing to be just 90% confident. And so now, with our previous study having an estimate for P to be P hat of 0.25, I'm going to make use of that. So P hat's 0.25, Q is 0.75. Remember, you can remove the hats there. For 90% confidence, the Z star changes to 1.645. That's on top. The desired error is 0.2. Calculate this through and you should get 13. And so N is just 13 in order to achieve this minimum amount of error, or sorry, maximum amount of error, and with just 90% confidence. So I wanted to demonstrate those just so that you've seen them. It's not a huge part of the course. You'll probably see very little of this again, but I think it's an important one in practice to know how to do. It's coming up, our hypothesis testing, another inferential technique.